So guys, this is 5-2 in Advanced Algebra 2, and it's a real kind of weird lesson. We're going to have to go back and forth between Desmos and the actual video. So I know you're on the video right now. Here's your practice worksheet. I emailed you a Desmos code, and I hope that we realize that I've kind of made some mistakes on this practice sheet. Like, we're going to do some paperwork when we get to Desmos on slide 7, slide 8, and slide 9. But for right now, I'd like you to just kind of go to Desmos, right? So you can pause the video and go type in that code and get yourself to where you get to this screen, okay, to where you're on slide 1, and then come back with me, and we'll do number 1 and number 2 together on Desmos, okay? So go ahead and get logged in. Alright, so now that you're back on the video, what I'll have you do is just kind of watch me do slide 1 and slide 2, because there's no way that you can watch this video and do Desmos at the same time. The screens will just be too small if you split the screen. So it's a real simple thing, but I just want to explain slide 1 and slide 2 to you. So what we got is they have given us a graph, and they want us to write the function in factored form right here. They've just got these number signs in place of it, and they want us to replace the numbers with what they're supposed to be. Well, you need a little explanation on that. Since this is in factored form, like each quantity is where one of the zeros is at. See, this x plus 5 is one of the factors, and you can see that the graph crosses the x-axis at -5. Since the 0 is at -5, that's why this is x plus 5, because -5 actually makes that guy 0. And another interesting thing to see is because since this graph actually crosses over the x-axis, that's why that quantity is raised to the first power. So if we look over here at this second place, that's at -1, -2, -3 right there. This 0 is at -3, so I need to go in here and change this pound sign. You can just watch me instead of doing it back and forth, so just watch me. I need to change this pound sign. Since the 0 is at -3, this thing needs to say +3 right here, just like this. So, and again, this quantity is not being squared because that guy crosses over. There's only one 0 there. And then as I move to the right in this little equation that they have typed out, they've got a 0 over here at 1, right? So that's why this says -1. And we just need to replace this other pound sign with, since that 0 is at 5, it's supposed to be a -5. And you saw that when I did that, this blue graph actually showed up right over the top. If I had put a different number in, like I say, I made a mistake, like I put 4 instead of 5, you see how the blue graph doesn't match right on top of that green dashed graph. So that's what they're looking for. So I'll do number 2 for you also because it's a little weird. So we'll go here to the next slide. And they say replace the pound symbols to make this. So it's again where at all the zeros are at. So if I look at this first 0 right here, it's at -1, -2, -3. So I need to do the opposite because -3 is what would make this guy 0. And because that guy crossed over the x-axis, that quantity is being raised to the first power. Then this other 0 right here, it is at 1, right? So, excuse me, it's at -1, so that's why this says 1. But notice that the graph actually just touches the x-axis, but it never crossed over. That's why that quantity is being squared, because it's like a double root right there. So that squared is like how many zeros you'd get in that case. And then if we go over to the last pound sign that they want me to replace, it is a 5, right? So that means I need a -5, and it should only be raised to the first power because that graph crosses over. So I did these first 2 with you. You can go to Desmos now and you can punch those in and make sure you get them right. And I also then want you to do slides 3, 4, and 5 and 6 by yourself. Like, just give them a try, mess around with it. If you make a mistake, big deal, you know, I could help you, or your teacher can help you. But stop after slide 6, okay, and then we'll do slide 7 together. So you can go ahead and pause this video now, go to Desmos and do slides 3 through 6, and then when we get to 7, we'll do that together. Okay, now we're on slide 7, and again, you should just kind of watch me do this problem, but you'll need your piece of paper. Like now it's time to finally do something on the practice sheet. You shouldn't have done anything on the practice sheet yet. We're on slide 7, and they want a little bit of work, so I have it visually for you. You can watch me, and then you can go back to Desmos and actually do this problem. But we'll have all the work done on paper. They say, all right, they want us to write an equation here, like if this was Desmos in row 1 for the polynomial function in factored form, and it's got to match this graph below, but it's got to go through this point 090, and we don't know what A is. So better start off with what factored form basically looks like. You can write, don't need to write this down, but factored form of a polynomial will be like y equals some A value times all these different parentheses. Like it depends on how many x-intercepts you have. So you can see that this graph right here in particular has 4 different x-intercepts at these pink spots. It doesn't matter about their like touching or crossing at this point. There's just 4 different x-intercepts. That means that I need 4 sets of parentheses in that case. Okay, so however many x-intercepts will need parentheses. And since this dude right here is at -3 for a 0, that means that I will go down here, and in my equation, you can write this down with me now, that this would be x plus 3, because -3 makes that 0. Also then, you got to realize if this guy touched or crossed the x-axis, since he only touches it, that means you need to square that quantity right there, because it counts for a double root. Then I'll move on to the next one. That's got a 0 at -2, so that would be at x plus 2 is the factor of that guy, and since he crosses over, we don't need to square it. It's only going to have 1 0 there. And then over here, this is at 4, so we'll have a group of x minus 4. And it's to the first power because it crosses over, and this is x minus 5 because that's got a 0 at 5, and it's also to the first power. So this is almost the answer that they want. The only thing that we don't know is this darn A value right here. So what we have to do is this ordered pair that they gave us, they said, hey, the graph's going to go through 090. We need to use it. And we know ordered pairs are written x comma y, right? So what we'll do is we'll substitute 0 in for x and 90 in for y into this equation so we can end up solving for A. So we'll do our work on paper right where they wanted us to here. Here's a y, and I know that that's 90. I don't know A because they're wanting me to find that, but I just need to now substitute in for x, and dude, we got a beautiful number. It's 0, right? So I can put 0 in for x, and if I did that, would you believe that this right here would just plain old turn out to be 3? And yeah, it's getting squared, but 0 plus 3 is 3, and here this would be 0 plus 2, which is 2, and this is minus 4, and this is minus 5 because we're putting 0 in for x. So that's really, really nice. Then all we got to do is solve for A, so we can punch all this stuff into our calculator. Let me get out of this. So I'll clear all that out. We'll get 3 squared. I'm just going to go ahead and call it 9 right away, times 2 times minus 4 times minus 5, and boom, we get 360. So we'll just clean that up a little bit. 90 equals 360 times A. And awesome, we can totally solve for A now by dividing 90 by the 360. And it's cool if you get a decimal. That's a nice clean decimal of 0.25. I'm also fine with the fact that if you want to call that 1/4, great, you know. But this is not still the answer they want. They want us on Desmos. So when you're done with watching me do this one problem here, you'll go to Desmos and you'll type y equals. Yep, we'll type that. You know, you might not have done that before, but it's different than our TI-83s and TI-84s. We can actually type the y equals, and then we'll put our A value of 0.25, and then we'll go back and put all these parentheses that we had before again. So the x plus 3 quantity squared, the x plus 2, it was just to the first power, the x minus 4, and the x minus 5. You punch that into, sorry, minus 5. You put that into your Desmos, and boom, you'll get your graph to lie right on top of that. Right? So that was on slide 7. We'll do the work. Then as you go forward, you'll do slide 8 and 9. You'll need to do this work also. So you do the work on paper, like we have back here. You'll do work 8 here and work 9 here. There is no work to do on slide 10. Like I said, I kind of made a mistake when I typed this practice sheet out. So you do that, and then once you get done with even slide 9, once you get done with slide 9 on Desmos, then just keep going. Finish the activity. There's nothing left to do on the practice sheet or anything like that, but just go through the slides. The rest is pretty self-explanatory. It will kind of help you. And then once we're done with all of this, then we'll go back to the practice sheet and finish watching the video. So you need to go to Desmos now and do slide 7, which we already did, 8 and 9, and then just finish it and then come back to me here on the video. All right, so hopefully we got the Desmos done now, and it talked about in those last slides after we did all the A-value stuff about relative mins, relative maxes, extrema, and turning points. So let's kind of dive in right here. What they didn't talk about yet was the absolute min, the absolute max. So a relative min or a relative max is where the graph turns around. There's those turning points, right, where it goes from increasing to decreasing or vice versa. But the absolute minimum of a graph is like as low as it possibly goes. So I like to ask bonus questions on this before we even get started. Is this guy got an even degree or an odd degree? And since it's both ends go in the same way, that's even. It's an even degree. And the leading coefficient, since both ends go down, should be negative. Well, this dude goes down forever, right, in this case. So the absolute min, like you can't go down to negative infinity and call that the minimum. Like the lowest this graph goes, it's just going to keep going on forever and ever and ever. So when it comes to an absolute minimum, this guy has none, is what we'll put in that spot. But it does, I'm going to skip around a little bit, it does have a relative minimum, like this point B. It is a relative min. It's not the lowest the graph ever goes, but it is relatively like just a minimum somewhere, any minimum you got. Then back to the absolute max. The absolute max is as high as this graph ever gets, and you can see that this dude never goes up to positive infinity. So it's these points right here, A and C. And yes, we could kind of argue that it looks like C is just a little bit higher than A. I'm not going to be that picky for you, but the absolute max of this graph, we'll say point A and point C in this case. Then the relative max is just anywhere that happens, so it's kind of like a repeat, A and C in that case. So relative maxes are any maximum points, and the absolute max is the highest it ever got. So we'll get better. We got more problems to do. Then the number of x-intercepts, that's pretty simple. We'll just count them up. So 1, 2, 3, 4. They're not even talking about the zeros there. They're not asking like did they count once or twice or anything like that. They're just like how many times does it touch the x-axis? So that is 4 times. This question is asking you about the points of tangency. Remember, that's where it just touched the x-axis, but it never crossed over. So this crossed over, this crossed over, this crossed over, and this crossed over. So there are 0 points of tangency. Then the turning points, that's where it turns around. Easy way to do that is just count up your relative mins and relative maxes. There are 3 turning points. And the last thing that's a little new on today's worksheet is the minimum degree that this polynomial could have. So let's make a little note here. There's an easy way to find the minimum degree. It's the number of turning points. You want to probably write this down. Turning points, and then add 1 to it. Right? So if you know how many turning points you do, you just add 1 to that, and that's the minimum degree. So since this guy has 3 turning points, we'll add 1 to that and get 4 for the minimum degree, which is awesome because that's an even number, just like we said that this degree was even. I would also like to preview some things that we're doing here in a little bit is to see if there's any like imaginary zeros, and that answer is no, because whatever the degree is, that's how many like total like zeros you'll have, and you find that with your x-intercepts and your points of tangency. So you add these together and you get 4, and if that's the same as this, then there's no way that you got imaginary zeros. So we will get better at that imaginary thing here as we go along. So let's just keep trying. First, I like to add bonus questions, even or odd. And since these ends are going different ways, this is an odd degree polynomial, and it's downright negative in that situation also, so this has a negative leading coefficient. So when it comes to that, is there any absolute minimum? No way, man. This thing goes down forever, so that it goes down forever, so there is none on that. And the same thing with absolute max. This thing goes up forever, so there's none there. There's no way that an odd degree polynomial could have an absolute min or max because they go to infinities both ways. But the relative mins, those I think we're pretty decent at. A and C, right? That's where it mins out somewhere. Doesn't matter. And the relative maxes are B and D. Number of x-intercepts, just count them up. 1, 2, 3. Nice. So there's 3 of those, sorry. 3 of those. Were any of them points of tangency? This crossed over, and this crossed over. So 0 because the points of tangency are where it just touches. Number of turning points, we add all these up, or you can go back to your graph and count them. There's 4 of those. And the minimum degree is turning points plus 1. So that means that has a minimum degree of 5. Terrific bonus question. Are there any imaginary zeros? Well, if the degree is 5, it's supposed to have 5 zeros. And right now, I only see 3 of them. 1, 2, 3. And none of them were points of tangency where they counted again. So the answer is, yeah, dude, there has to be imaginary zeros. And when you get super experienced like us math teachers are, you can see where they're out in the graph. Like the imaginary zeros is where this graph twists and twists and twists and turns around, right? You got all these turning points, but notice when I highlighted through all those turning points, I never ever crossed over the x-axis. That's where the imaginary zeros are at, is where you twist, 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 or turn, 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 and you never touch or cross the x-axis. So, weird. Let's try again. Absolute minimum of this graph, since he is even, it's possible for that to happen. With a positive leading coefficient, that will happen. The absolute minimum is just C. A is not an absolute minimum. C is as low as it goes. The absolute max, there is none, because this dude goes up to infinity. Relative mins, though, that's where we list A and C. And the relative max, that's just the B, somewhere where it maxed out. So, sorry. My pen freaked out there. Number of x-intercepts, boom, boom, the dose. Were any of them points of tangency? Nope. This crossed over the x-axis, and this crossed over the x-axis, so that didn't work. Number of turning points, we can go count them if we want to, but it's just these 3 guys right here. And the minimum degree of this guy is turning points plus 1, so that is 4. Are there imaginary zeros? Well, the degree is 4, so there's supposed to be 4 zeros, but we only see 2 of them, right? So there has to be, and you see how it twists and turns around, but this never crossed over the x-axis. So there are imaginary zeros in that, and we'll get better at that as we go along. That's still really weird. So why don't you pause the video and give just this part a try, just the top part. See if you can do the absolute min, max, relative, mins, and max. So pause it and give those a try. There is an absolute min at A. There is no absolute max. The relative min is also A, and there is no relative maxes either. So that can happen, big deal. Number of x-intercepts, we'll count them up. That is 1 of those dudes. The points of tangency, that is a point of tangency, so we'll count them, and there is 1 point of tangency in that place. So, cool. Number of turning points, well, we go and find them, and it's just the 1, right? It's just A is the only turning point. So the minimum degree is turning points plus 1, and that would be 2. Are there any imaginary zeros? Well, we add these together because there's 1 x-intercept here, and you add that with your point of tangency, that adds up to be 2, and since that equals your degree, there are not imaginary zeros in this case. So we'll just keep on practicing with that. The cool thing is we'll do that on these last 3 problems. Here's like all these parts, A, B, C, D, E, F, G. These are the questions that they're asking you. What we're going to do is we're going to take a little bit of notes right here. So we're going to write some notes down before we go end up doing those problems. So if they ask you if the leading coefficient is positive or negative, wouldn't you look at the graph that they have for you, and it's what would you look at? Yeah, you'd look at the ends. It's the end behavior. So we'll put a little notes back here, so that way when we're looking back and doing homework, if they want to know if the leading coefficient is positive or negative, you just look at the ends, if they're going the same way or different ways. That's the same thing as if they want to know if the degree is even or odd. Don't you look at the end behavior in that case? So we're checking out the ends. But the constant term, We haven't talked about that in a long, long time. They want to know if the constant term is positive or negative. Well, check this out. Like, if I go old school and just put this line right here, this is a linear equation. Like, the constant term is this guy. He is constantly 3 because he doesn't have a variable. Isn't that the y-intercept right there? So we totally just need to check the y-intercept. It doesn't matter if it's a line, or if it's a parabola, or anything like that. The constant term of any graph is all about your y-intercept. And you just check to see if it's like a positive or a negative number. So that stuff, okay. Then the degree. I know we're still new at this. It's no big deal. This is why we're taking notes. Don't feel like pressured to like you have to understand this right now. We're still practicing. But the degree has to be greater than or equal to what? We would count the turning points and add 1. Sorry, I need to, my bad. Turning points plus 1 is what that says. I kind of got cut off by my little deal there. So to find the degree, you do the number of turning points and add 1. And we'll keep practicing that as soon as we get all these notes taken. How many distinct roots are there? The roots are the zeros. Dude, those are our x-intercepts. We'll count those up. So it's the number of x-intercepts. If I'm going too fast, you can always hit pause. And if how many roots have even multiplicity? Even multiplicity is like a fancy way to say that double root thing, you know. And that's where we're looking at the points of tangency. You don't need to write all this down, but you probably want to just count your points of tangency. I think we understand what that is. So that's how you tell if they're even multiplicity. And then this part G, the must there be imaginary roots. Let's write this down. Like I said, we're just taking notes, and it'll make a million times more sense when we start doing some problems. So here's what we're looking at to see if there must be imaginary roots. We look to see if part E plus part F equals part D. Like the answer we got for part E plus the answer we got for part F, if that equals part D. That's what we're looking at. We want to see if the number of x-intercepts plus the number of points of tangency equals the degree. So pause if you need to get all this written down, and let's go do some problems here. I personally like to do part B first. I want to check to see if this thing is even or odd. So I'm doing part B, even or odd. This thing is even because those ends are pointing the same way. Then I go back and do part A to see if the leading coefficient is positive or negative. Since it's going down, we'll write positive. You can abbreviate, but just don't put a plus sign. Like let's put this. Oh, that's my bad. It's negative. Sorry. I bet you were all freaking out there for a second. This is negative in this case because they're both going down. And don't just put like a minus sign, you know, like put NEG for negative. Part C, that's the weird part. Is the constant term positive or negative? We're supposed to be looking at the y-intercept. So here he is. There's the y-intercept right there. And would you believe, since he's below the x-axis, that that is negative? Part D, the degree must be greater than or equal to what? So we need to look at the turning points and add 1. So count them up. There's 1, 2, 3 turning points. Add 1 and 4. Awesome. How many distinct roots are there? That's the number of x-intercepts. So I'll go count those up. Here's 1 and there's 1. All right, there's 2 x-intercepts. Were any of them points of tangency? Like, did they have even multiplicity? And that's no, so 0 of them did. And they say, must there be imaginary roots? So we got to do a little opposite game here. So we're supposed to check if part E plus part F, if the number of x-intercepts plus the number of points of tangency equals the degree. So let's do it like this. Yes or no? Does 2 plus 0 equal 4? No. Opposite. Yes, there must be imaginary zeros. Because we said no to that question, we will put the opposite answer, like the number of x-intercepts plus the point of tangency needs to equal the degree for them to not be imaginary. So we said no to that question, we'll say yes to this. So let's try another one. That was weird. Even or odd? Even. Both ends point the same way. Kind of leading coefficient? Positive in this case, which you can abbreviate like this. Then what is the constant term? Well, that's the y-intercept. So that is 2, which is a positive guy. They want to know if he's positive or negative. The only time you can't answer that is when it's 0. So like if that was 0, we would say that it is like neither positive nor negative. D, degree is equal to the turning points plus 1. So 1, 2, 3 turning points plus 1 more is 4. How many distinct roots are there? That's counting our x-intercepts. There are 2 of those. And how many of those were points of tangency? Well, this one and this one. They're both points of tangency, so there's 2 of those. Does this plus this equal this? Yes. Opposite game. No is the answer to this question because there are no imaginary zeros. Like you can see that didn't happen. I want to go back to this. Oops, my bad. Go back to this one. Did you see where they're at? Do you see the twist, twist, twist? And that thing never crossed the x-axis there. So that's cool. And this is the last one, right? Nope, yeah, last one, I think. Why don't you get her done? Why don't you pause the video and see how we do? Okay, here's what I got so far. This guy's odd because the ends are going different ways. It's got a positive leading coefficient because it's positive upright. The y-intercept is at 0, so it's neither even or odd. My degree, I counted 6 turning points, so I added 1 and got 7. Remember, these should match up also. It's an odd degree. 7's an odd number, so that's good. And then 5 was how many x-intercepts I counted. None of them were points of tangency, so must there be imaginary roots? Does 5 plus 0 equal 7? No, so opposite, and we'll put yes in that case. So you can see where they're at. It's twist, 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 twist. So what a weird video. We had to go back and forth between Desmos. If you had questions, that makes perfect sense. Come see one of us. We will definitely help you out with that. And let us know. Have a good one.